morning, everyone. So I thought we'd start off with a group exercise. And we'll be good. So I'll give you about 15 minutes to kind of work on it, but let's talk about it real quick. So this says we have particles 1 and 2. Each one has a charge Q1 equal Q2, which equals 2e. Remember, E is the fundamental charge, so it's 1.602 times 10 to the minus 19 coulombs. Are along the y-axis, where the first one is at a positive y distance, the other one's at a negative y distance, but they're both at the same distance, d, where d is equal to 17 centimeters. And then we have a third particle, which has a charge of 4 times e, so again, that's the fundamental charge. And this guy's going to be moved along the x-axis here, starting at 0, and is going to move along here, finally finishing off at 5 meters. So what we want to know is at what values of x will the magnitude of the electric force on this third particle from the 2 other particles be 1 a minimum and then 2 a maximum. Then we want to know what are the actual values of the force at these locations. So let's kind of draw what's happening and then we'll talk about it some more. So here what's happening is, again, I have my y-axis here. Here's my x-axis. So we have one particle here. This is Q1. Second particle here. This is Q2. Distance D. And we've got a third charge somewhere here. So it's Q3. So let's talk about the forces and all that kind of good stuff. So here, this distance from here to here is going to be the distance r. This distance from here to here is also the distance r. So those are the 2 distances r's. So let's think about the force. So all of these guys are positive charges, which means should I have an attractive force or a repulsive force? So if they're all positive charges, should it be attractive or repulsive? Repulsive. So what'll happen is, from the top one here, this guy's going to feel the force down in this direction. So it's going to be F top. And then from this one down here, this one's going to feel the force in this direction. This is then going to be F bottom, let's call it. Right? Now what I also know is this angle here is the same as this angle here, which is the same as this angle here, which is the same as this angle here. Right? All those angles are the same. Now the other thing I know is, well, since this charge is the same as this charge, this distance r is the same as this distance r, what that tells me then is that this magnitude of the force here is the same as this magnitude of the force here, which means what should happen to the vertical components of the force? They're going to cancel, right? So the only thing that's going to happen then is the total force on this guy is going to be along the x-axis. Right? So this is going to be the force on the third particle. Now what should happen then, though, is when the particle is sitting here, what should be the net force on the particle when it's sitting at the origin? 0, right? It's going to feel a force downward and a force upward, but those 2 magnitudes are going to be the same. So the location that's going to have the 0 amount of force is then going to be at the origin. So what will happen then is as you start moving away from the origin, the force then is going to grow. This force is going to get bigger until eventually it's going to reach its maximum, and then it's going to decrease and go to 0 at infinity. And we can plot this later if you want to, but basically what we should expect is that the force plotted as a function of position, so this is F3, is going to be 0 here, it's going to rise up, go to maximum, and then eventually taper off and go to infinity here. So you're looking for this location here. So this is going to be x maximum, and this location here will be x minimum. Okay. So to do this problem, again, all you need to know is the cosine components of each one of those 2 forces. So the trick here is to rewrite cosine in terms of the geometry, right? Because what happens? As this particle goes further and further to the right, or more and more to the left here, what happens to the angle? Well, the angle changes as x changes, right? Because if I move it in this direction, what happens then is the angle becomes greater, but if I move it in this direction, the angle becomes smaller. Right? So instead of using this angle here, use this angle here to rewrite this angle, or at least cosine of that angle, in terms of the geometry, meaning rewrite it in terms of x and r and d and all those different things. Okay? Once you do that, how do we find this maximum location? Take a derivative, right? In respect to x, set it equal to 0, solve for that position, and then there you go. Okay? So I'll bring up the actual question again. These are the solutions. So we should have that the minimum location is 0, maximum is d divided by the square root of 2, which means the minimum force is 0 and the maximum force is that guy. So I'll give you about 15 minutes to kind of discuss amongst each other, figure out how to write the cosine in terms of geometry. I'm mostly doing this problem now because when we get to starting to do integrals, we're going to do this all the time. Because these angles are going to be functions of positions, and we're going to have to integrate over positions, so we're going to have to do integrals over them. So we can't just leave it as cosine theta. Because as the position changes, the angle changes. So those two are functions of each other. So I'm going to figure out how to do that now, so by the time we actually do it together, it'll be nice and simple. Okay? How's that? Give me about 15 minutes, kind of walk around, check on everybody, and then we'll start talking about fun stuff. Electric field. And this is already up on Blackboard, so you don't have to copy it down. Oh, no, it's any random x. Right, or some angle, and then parameterize it in terms of x. So we use. So this is the adjacent side is the x distance. Now we know r though would be the same thing as the square root of d squared plus x squared. So now put those two things together. So it means cosine of theta is going to be x divided by the square root of 17 squared plus x squared. So now that's where x is going to be introduced there, but you also have another r squared k times q times q. So put all that together, take a derivative. Okay. What can I help you? So much. So draw me an angle here. So we're going to use that. So what is cosine of that? Good. So according to that angle, what's the adjacent side? Good. So let's write that down. So we write cosine x divided by this is what I want. So how can I rewrite r in terms of x? So with that, you're seeing. So the r is also simultaneously x squared plus y squared. I get it. So let's write that. So that's going to be equal to that x divided by the square root of x squared plus squared. There we go. Oh, square. So finally, that is then the cosine portion. And then we put that back to the force. The force says that is equal to k times q times q. PHYS, that's 2E. And then put all together into the derivative. So now you go back into the rest of this, into the form. We're taking the derivative of 4. Right, we'll put this portion, so this is the cosine portion. We're going to multiply that by. Because we're maximizing the 4. Good. So that's the magnitude of the force. Almost. That's magnitude of the force. How many do we have? 2. So 1 out of 2. Because they're both given to the same. So we want only the cosine portion of that. And then we'll talk about it. So we want only the horizontal piece. Yes. We'll leave that the way it is. Now it's cosine. Good. Now what you want to do is rewrite cosine theta in terms of the geometry. So using this angle here. So what's cosine definition? What's that? Adjacent over x. So according to that angle, what's the adjacent side? X. Good. And what's the hypotenuse? Good. So now we're going to we'll do it instead. Good. So now on the next line, we got all this. Yep. Times x. So we're by r. Original r is the square root of x squared. We take the derivative and then subtract. That would have to derivative. Well, what do you mean by that? Oh, yeah. Yeah. Over here, square root. Yeah, all that stuff is constant. You over here, the square root. Square root. Good. Yeah, so basically, you're going to get the derivative of x divided by x squared plus b squared to the 3 half power. Oh, okay. So we don't want to write this in the actually, we want to write in terms of the geometry. So use this angle here, and then rewrite cosine. So cosine by definition is what the adjacent over the hypotenuse, right? According to that angle, the adjacent is x. Good. R, but then we know R in terms of x and b. No, you're both gonna be dirty looks. Meaning to you, forces. Yeah. Yes, like that. So this is the force from this one. Yeah. Yeah. Well, you already have the angle. No, you're good. So we have to take a derivative. Because when I want to find this location here, the slope of the derivative here has to be equal to 0.
Okay, so what are we using this for?
Because as we're looking at it, the vertical portion of concentrations some of those two is only the sum of the x portions. So that's when it's only the horizontal.
And we use that where?
So now we have F3 k times q times q divided by x squared. now I have two rows. But again, I want only the cosine.
So you're just
Yes. I'm going to rewrite that R squared. Here, K and 2 and 4. That's 2E times 4.
I don't think I'm.
Okay, that's a fundamental charge. So 1.6.
Okay.
So K2, 4, E squared, and 2 are all constants. So you can get rid of those. And then just take care of it. So Q1 is just 2E, and Q2 is Q3 in this case, which is 4. Yes, yeah, because it's the force on 3 by 1, and the force on 3 by 2.
Yeah.
The force on 3 by 1 is the same as the force on 3 by 2. But, so that's just but it's yeah. Yep. So the vertical force is 2, the forward force is
Oh, yeah. Yeah. So there's
correct. Yeah, for both. So it's that one plus that one, which is the same.
okay. Yeah.
Good, yes. So sometimes the derivative of x divided by x squared is b squared to 3. Kind of a nasty derivative. We don't do the derivative either. From the question. We still need to multiply this by 2. Now to take a derivative of that. So this is supposed to be -1, and then so now we're supposed to Well, we'll go through this. Oh, yeah. Let me help you guys. Let's do it. How close was it? All right, now number one thing about derivatives is never, ever, ever use the quotient rule. I don't know why they even teach that, because that is just ridiculous. Everything is a product rule, right? Easiest way to do derivative is product rule.
Oh, yeah.
So here we're trying to take a derivative of d dx of, so x divided by x squared plus d squared raised to the 3 halves power, right? Again, I don't know why they bother teaching the quotient rule because it's just stupid, but anyway. My opinion. Anyways, so let's rewrite this as a product rule, right? So this is d dx of x times x squared plus d squared raised to the minus 3 halves power. Make our lives a little bit easier. So now what we have is a derivative of two functions. So we're going to take the derivative of that times that plus the derivative of that times that. Or the product rule. So it's simply going to be x squared plus d squared raised to the 3 halves power. That's the derivative of the first times the second, plus the first times the derivative of the second. Well, if I take a derivative of this, the minus 3 halves comes down. So this becomes what? Minus 3 halves times then x squared plus d squared raised to the minus 5 halves, because I minus 1 from that, right? Times the derivative of the inside, where the derivative inside is simply 2x. Okay? Good. So let's rewrite this. So this becomes, oops, I need a negative sign there. So this is 1 over x squared plus d squared to the 3 halves. This 2 is going to cancel this 2, so it's going to become minus x divided by x squared plus d squared to the 5 halves. Okay? Okay? Common denominator is simply x to the 5 halves, so let's multiply top and bottom of this one by x squared plus d squared. So finally, this is going to become x squared plus d squared minus, switch back, so it's going to be minus x, right, divided by x squared plus d squared all raised to the 5 halves. Assuming I multiplied all that stuff out right. Oops, I forgot my 3 here. That's a minus 3. Sorry, minus 3. You doing okay? Now, since all this is equal to 0, do I care about the denominator? No. The only way the denominator causes this thing to go to 0 is if x goes to infinity. That's the only way, right? So since all this is equal to 0, I'm going to multiply that guy over there. I feel like I'm missing a term. Where did I go? Squared, e squared. Oh, I have an x here and an x here. Sorry, that should be an x squared. There we go. That makes it better. Good. So for this thing to go to 0, the numerator has to go to 0, which means I have x squared minus 3x squared plus d squared must be equal to 0. So that's the same thing as what? D squared minus 2 times x squared, which means x squared then must be equal to d squared divided by 2, which means that x then must be equal to d divided by the square root. All done. So, number 1 rule, never ever use the quotient rule. That's the best thing I can say. Everything's a product. All right, everybody's doing okay? So good, so this is your x max. X min, we already argued, was equal to 0, so now just put this guy back into your force expression, and then that gives you the maximum force. Okay. Molly doesn't believe me. Correct. So now if you want the maximum force, all you're going to do is say that F max is equal to the 2k q1 q2 over r squared, which again is x squared plus d squared times x divided by the square root of x squared plus d squared, all evaluated at x is equal to d divided by the square root. That's then F max. Class is always funny because when I do stuff like that, you all look at me like I'm doing magic.
Just teach you how hard ways to do it. Tell me like slick, easy, no shortcuts. They want us to feel the pain that they've suffered for years.
Probably. You guys remember, subtraction is addition and multiplication, and division is multiplication. That's all we need to know. So that's just the force expression that you had originally. And now I'm simply going to evaluate that at the maximum position because that's the maximum force, where the maximum position we just found was d divided by square root of 2. I'm just plugging it back in. Yeah. Everyone's okay? You look confused, Corey. You doing okay?
Somehow I have a bunch of different numbers in my equation. I have a 2, a 2, and a 4.
Oh, no, you have those because Q1 is equal to 2e, Q3 is equal to 4e.
Oh.
So if I put all that in
I
there,
didn't know what that was. I thought that was a 9. It's a Q.
that's a Q. Is that better? Okay. Good. So if I wrote it all out properly, then this would be what? 16k times e squared times x divided by x squared plus d squared raised to the 3/2 evaluated at d over square root of 2. What's wrong? It's just bad. That'll be great. Always cracks me up when you have foreign professors. A lot of times they say you should have learned this in high school. They actually did learn it in high school, but that's what's done. Especially Russian and Japanese and Chinese. Anyways, everybody okay? Feeling okay about it. Great. So I'll let you put all the rest of the pieces in. So let's talk about some new stuff for today in our last 20 minutes. So the next thing we're going to talk about is this idea that charged particles put a force on each other from spatially distance away, meaning that, again, these guys were separated by a center-to-center distance r. Let's say they're like charges, so that these guys had a repulsive force acting on them, even though these guys were not in direct contact with each other, really bothered physicists for a long time. They didn't like the idea that two things could interact with each other at a spatial distance. They wanted them to actually be in direct contact with each other because that makes sense. And again, the floor is holding me up because I'm in direct contact with it. I move the controller because I'm in direct contact with it. They didn't like the fact that two things could actually interact via spatial separation. So the resolution to this, they spent a long time kind of thinking about this, but the resolution came from a physicist by the name of Michael Faraday. We're going to see that name later in this semester. But what he proposed was the presence of what's known as an electric field. So what he said was that every charge generates a field called the electric field, which is a disturbance throughout all space and the force is the result of the interaction between the electric field and the charge, the other charge. So this was his proposal. So what he said was that anything which has a charge creates a disturbance. This disturbance then penetrates and propagates throughout all space, which means it has a value at every location in space. Then the force that another charged particle would feel would be then the interaction between the electric field created by the first charge and that second charge itself. So inside of here, we have to talk about some things. First of all, what is a field? Because if we have an electric field, we have to have a field, which means we have to understand what a field is. Well, it turns out there are two different types of fields in general. There's actually more types of fields, but as far as we're concerned, we're going to have two types. The first type is what's known as a scalar field. A scalar field is a function which has a value at every location in space. This is a scalar field. So this is a function which has a value at every location in space. So to know what the value of the function is, I have to know where I am. So for different locations, I have different values of this function. So let me give you an example of a field, or at least a scalar field. A temperature map. This is a scalar field. So what a temperature map says is, here's the temperature map of the US. What this says is that every location here, this is longitude and latitude, every location then corresponds to a temperature. That temperature is then given by this temperature field. This would be a field, okay? So at every single location in space, I have a different value of the function at that different value of space, which means that the field depends on the position at which I am in the space. This is a scalar field. Okay. So things like temperature fields, pressure fields, things like this, these are scalar fields. The second type of field is what's known as a vector field. A vector field is a function which has a value and a direction at every location in space. So what this means is it's one step up from a scalar field. It's a scalar field, but it has a directional property associated with every point as well. So what this means is that at every location in space, there's a value and a direction associated with it at all of those locations. This is a vector field. Good example of a vector field is a wind field. So I can say that here in Evansville, the wind is blowing at, say, 10 miles per hour north. That's a vector field. Every different location has a different value of the field, but it also has a directional property associated with it as well. So, for example, we can say that somewhere around here, this is around Tampa Bay, Florida. This then has a magnitude of, which is going to be somewhere around between 30 and 40 knots. And then the direction at this point looks like it's kind of pointing southish. Or we can go somewhere, let's see, where I want to go, Texas, so somewhere around like Dallas is somewhere around here. This direction, if I can make out that arrow, looks like it's pointing north, also around 30 to 40 knots, and etc. So California, we have what? LA is somewhere around here, I think. So again, this one is kind of pointing this way-ish, so that's going to be northwest, or sorry, northeast. So this is a vector field. A vector field has a value and a direction at every position in space. It exists everywhere. The value may be different, the direction may be different, but it exists everywhere throughout the space. This is a field. Okay? So again, we have two types of fields. We have a scalar field, which means it has a different value at every location in space. Another one would be like a topological map, right? You have a different height at every location in space. or the vector field, which then has a value and a direction everywhere at space. So what Michael Faraday said was that to understand the force at this distance, what they used to call spooky action at a distance, is that this charge here created an electric field. This field had a value at every location in space. Then this charge here knew about this charge over here because of the interaction between himself and this guy's electric field. This is how we understand this property. This is also true for gravitation. Here I have this guy. This guy is interacting with the Earth. This guy knows to fall because the Earth is creating a gravitational field. It has a value at every location in space. Here the direction is downward towards the center of the Earth. So this thing knows that it has to feel an interaction because of the field based off of the mass of the Earth itself. Anything which has mass has a field. This is an electric field. So anything which has charge creates an electric field. Then it's the interaction between the electric field and the charge of interest, which then generates the force. Now, electric fields are, of course, vector fields. They have a direction and a value at every location in space. So an electric field then is a vector field which has a value and a direction at every location in space. I'll tell you how we actually determine that in just a second. So before that, I want to show you a quick video I made yesterday because I couldn't bring all the stuff with me to class, so I just had to make it up as we go. Life will be great. So hopefully you can see this. So here, this thing is what's known as a Van de Graaff generator. So what a Van de Graaff generator is let's see. Play with the lights here for just a second. There we go. So what a Van de Graaff generator is basically it's a motor down here, which then has a piece of felt, which is then wrapped around here. So the motor spins the felt, and then up inside of the globe up here, there are these little prongs that basically strip off electrons from the felt. Okay? So as this thing spins around, the faster the belt moves, the more charges are going to be stripped off. Okay? So what happened is, as I turn this thing on and it starts moving around, this globe then will become charged. It's going to become negatively charged, more specifically. Now, what I'm going to do here is show you kind of two things. So here is some rabbit fur, which is basically on here. So here, what you'll see on here is it'll start to stand up. The hairs will start to come off. I don't know how good the video is going to be. You can watch this on your own computer later. But then after that, I'll turn off the lights, and then I'm going to use this thing here, which is actually a light bulb. Now, what you'll hopefully see, which you can kind of see in the video, is I'm going to hold the light bulb near the globe, but not actually touch the globe, and then you'll see the light bulb start to light up. I'll tell you why that happens in just a second. So let's hope all this works. All right, so unfortunately, since I can't bring the demos to class, I have to kind of do them outside. It's something that's kind of interesting. So what I have here is what's called a Van de Graaff generator. So this is actually just a piece of felt just attached to a motor down here. That's going to cause this thing to spin. And then up inside of here, inside of this globe, there's basically just little teeth that are going to strip off electrons, causing this thing to become negatively charged. So basically what will happen then is this thing's going to become negatively charged, but as we talked about, there are charges down here. So then we're going to create a repulsive force between the two of these to then create an electric force. So here you can see the gears starting to stick up. They will actually start to increase. They will actually start to stand up. Not as impressive. But what's actually more interesting about this is the fact that what's really happening is this thing is creating an electric field, which means that this electric field, due to the fact that this is being negatively charged, creates then an electric force onto here due to the fact that I have charge inside of here, so charge in presence of an electric field manifests itself as an electric force. Now I'm going to do the same thing with this light bulb here. So basically inside of here, there's a metal, and there are electrons inside of this metal. So here I'm going to create again an electric field, and I'll hold this guy near here, and you should, hopefully, depending on how much light comes from the computer, see that this thing actually lights up. So give me just a second, we're going to turn off the lights here. I talked too much. So now we have our mood lighting on. So again, I'm going to go ahead and turn this thing on. There's the switch. So, then we get to a light bulb near here. So, trying to see it here, hopefully. There it is. Can you guys see that or not so much? Good, I'll tell myself to shut up. Great, so again, what we're seeing here is the fact that inside of this light bulb there are, get the lights turned back on, there are charges because of the fact that there's metal, right? So we know metal is a conductor, which means that there are free excess electrons which are running inside. So what I'm doing is by holding this thing near here, I'm actually then creating a force onto them due to the fact that they're sitting now in an external electric field. So as soon as that globe becomes, so as soon as the globe then becomes charged up, it then creates an electric field, and then by putting in the light bulb near it, I'm then causing the charged particles down here to accelerate more because they're closer to it, so they're both feeling a force. So these guys have a greater force than the ones that are up here, which means you're seeing this section more than you're seeing, and then it gets dimmer and dimmer as it moves away. So here, this is simply being lit up because I'm causing these electrons to accelerate. Now, at the end of the semester, when we start talking about light, we'll learn the fact that light comes from accelerating charges. So if I can accelerate a charge, I can actually get it to give off light. This is a source of things like cyclotron radiation, where in that case, you're causing accelerating particles to move in a circle, which means that they're giving off light in these cases as well. So anyways, the point of all this is an electric field. So the interaction of a charged particle with the electric field then manifests itself as a force. So how do we then determine the direction of the electric field? Well, typically what we're going to do is we're going to take some region which has some pre-existing electric field, and we're simply going to drop in a point charge. So I'm going to drop in a little charge here, which then has a little charge Q. This is what's known as a test charge. So little Q here is called a test charge. And we're simply going to watch what happens to that charged particle. So let's say if I put it here, it might follow a path that does something like this. So what we do is to determine what the electric field looks like is at every location, let's say if I'm looking here, I'm going to measure the force on this charged particle. So at this location, the force will point off, say, something like this. So this is the force. At this location here, my force then will point off, say, something like this. This is the force. At this location here, my force then will point off something like this, and etc. Or maybe I drop it at this location here. So this is Q. And now it's going to follow some slightly different path. So now it's going to do, say, something like this. So again, at every location, I just simply look at the force. And then we define the electric field from the force. So we then say that the electric field is equal to the limit as Q goes to 0 of the force divided by the charge. This is our definition of the electric field. So the way we determine the direction of the electric field is we're simply going to say at every location where we measure the force, the electric field then is the force per unit charge at that location. And since Q here is always a positive number, what that means then is that the electric field points in exactly the same direction as the force itself. So that means that at all these different locations, this is then the direction of the electric field. So by watching the motion of the test charge, and by measuring the force at every location, we can then establish what the electric field looks like for this particular charge configuration, or at least for this region of space. Now, what does this mean? Well, we know then that force has units of newtons. We know charge has units of coulombs, which means the electric field then has units of newtons per coulomb. So this is the units of an electric field. Now, one quick question. Why is it important that I take the limit of the charge of the test charge going to 0? What does that mean in this case? Does this mean it's a derivative? Because typically when you see one thing divided by something else and you take the derivative of the something divided on the bottom going to 0, typically that's a derivative. Right? But is that what this means here? Is that what this means here? So again, if we think about velocity, remember velocity is equal to the limit delta t goes to 0 of delta x divided by delta t. This is the instantaneous velocity, right? So this means that this is actually equal to the derivative of the position with respect to time. Now my question is this the same thing? Does this mean that the electric field is the derivative of the force with respect to charge? Is that the same statement here? Like Matthew was shaking his head, no. Good, that's right. Not the same statement here. This is not a derivative. So what is an important meaning that the limit of the charge has to go to 0? Why is that important? Go ahead, Barry. Good. Basically, that's right. So the point is we want to put a test charge in there because if this charge is too big, that'll generate too much of a force on whatever is inside of here, creating the electric field, which means it's going to change the charge configuration. Right? So if what's creating this charge configuration, meaning what's creating this electric field, is due to the fact that I put some charges in particular locations, which means it's going to create a particular electric field. But if I want to test what that electric field looks like based off those charges, I don't want to move those charges. I simply want to put in a charge that's going to sample what's going on without moving those charges. Meaning I want the force on it to be as small as possible because I don't want it to change what's actually happening. Right? That's what this thing says. So the point that the charge has to be small is to ignore what's called back reaction. We don't want the force onto that charged particle to be the same as the force going back onto the original charge, causing that charge to move to a different location because that changes the electric field. So we don't want to do that. Okay? So this limit here has nothing to do with derivative. It just means that we're going to put in specifically a test charge, which is something very small. A very small charge. So this is how we define an electric field. So the electric field is the force per unit charge that exists at that location, meaning this is the force that this charged particle would feel if I put it at that location. That's what this means. This is the electric field. So it means that this location in space, this is the amount of force that this charged particle would feel if it existed there. That's the electric field. Again, it is a vector field, meaning it has a location. At every location, it has a magnitude, and it also has a direction as well. So that brings us to what are known as electric field lines. Let's talk about this real quick before we call it a day. So electric field lines. So electric field lines are a great way to visualize what is going on with an electric field. Okay? This is purely for visualization purposes. So electric field lines say that if I had a positive charge, my electric field then has to point radially away from my positive charge. This is my electric field from a positive charge. Again, reason for that is if I put a positive test charge near here, it wants to accelerate away from this charge, which means if I take the force on it, which is in this direction, pluck out that charge, it has to be in the same direction as him. If I had a negative charge, this means that it wants to be attracted to it. So this guy would have electric field lines going in and ending on the negative charge. Now the thing about electric field lines is as long as there's no other particles near it, they always have to move in straight lines, which means they have to start someplace and they have to terminate someplace. They start at positive charges and they terminate at negative charges. So usually we're going to call a positive charge a source of electric field lines, and a negative charge then is going to be a sink. This is the place that they terminate. So again, these are visual representations of trying to figure out what the electric field looks like in a particular space. So for example, if I had a positive charge and a negative charge in the same space, what do we know? Well, we know for the positive charge, the electric field lines have to radiate away from it. For negative charge, we know they have to terminate on it, which means I can determine the electric field for the entire space by simply connecting all these lines together. So for this guy, these two would have to be connected, these would have to be connected, this would be connected to him, this one would be connected to him, and it would look something like this. This is what the electric field looks like. So at any location, the direction of the electric field then will be tangent to this line. So in this case, it would be pointing off in this direction, and then its magnitude would depend then on the direction. So at this point, the electric field would point this way at this position. Another example would be, what happens if I had, say, two positive charges? Or one positive charge here, one positive charge here. Well, in this case, again, we know our electric field lines have to begin on positive charges. Now, what happens in this case, though, is electric field lines are not allowed to cross with each other, which means that since this is a source, this is also a source, there is no sink, so these electric field lines would actually have to diverge away from each other. So if I continue these guys, this one would have to go down this way, this one would go like this one would go like this, and diverge away from each other. This would be my electric field in this particular configuration. So we'll do one more example of drawing these guys tomorrow, and then we'll start talking about how do we actually calculate these things. So basically, your homework for tonight is to try to start coming to terms with fields. Okay? Because here on out, throughout the rest of the semester, we're going to be playing with fields. No longer are we talking about one thing that exists at one location in space. These things are fields. They exist at all locations. They have values at all locations. They have directions at all locations. So your job for tonight is to start coming to terms with fields. Now, if you guys are in Calc 3 or taking Calc 3, you already know what fields are. You should be quite comfortable with fields. That's pretty much all of Calc 3. But if not, life is good. All right.